Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this problem. So let's get started. So the problem is given as you are given two numbers x and n, and you want to count x to the power n. For example, if x is 2 and n is 5, then 2 to the power 5 is 32. And if x is 3 and n is 5, then 3 to the power 5 is 243. In previous video, we have discussed recursive approach to solve this problem. And the time complexity of recursive approach was theta of log n, and space complexity of recursive approach was theta of log n. Now in this video, we are going to discuss about iterative approach to solve this problem. And in this approach, the time complexity of our solution comes up to be theta of log n, and the space complexity of this solution comes out to be theta of 1. It means constant space. So before we move on to write solution to this problem, let's have a look at these facts. So the fact number 1 is that we can write any number as sum of power of 2 set bits in its binary representation. Okay, so let's understand this with an example. So let's say the number is 5. And the binary representation of number 5 is 0101, correct? So this is our least significant bit and this is our most significant bit, right? And here each bit is representing a power of 2. So it means our first bit representing the power of 2 as 2 to the power 0, our second bit representing 2 to the power 1, our third bit representing 2 to the power 2, and similarly the fourth bit representing 2 to the power 4. And what is 2 to the power 0? It is 1. Similarly, 2 to the power 1 is also 2, 2 to the power 2 is 4, and 2 to the power 4 is 8, right? So how can we write 5? Can we write 5 is equal to 4 plus 1? Obviously we can write 5 is equal to 4 plus 1, right? And we can also write 5 is equal to 2 to the power 2 plus 2 to the power 0, correct? So both are same thing. Now look at this closely. Now here this bit is set. It means we are simply adding the value of this bit plus the value of this bit, and we get 5. So this is the actual meaning of this line. It means we can write any number as sum of power of 2 set bits in its binary representation. So here this bit is set, and the value of this bit is 2 to the power 0. And next this bit is also set, and the value of this bit is 2 to the power 2. So when we add 2 to the power 2 plus 2 to the power 0, we get 5. Alright, clear. Now let's move on to next fact. And the next fact is we can traverse all the bits of a number from least significant bit to most significant bit in big O of log n plus 1 time, right? So let's understand this. So again, if we have 5, then the binary representation of 5 is 0101, right? And the value of bits are 1, 2, 4 and 8 and 8. We saw this before, correct? Now if I take a log of 5, we get 2, and we add 1, we get 3. It means to traverse the binary representation of 5 from least significant bit to most significant bit, we only need 3 steps. For this bit, for this bit and this bit. So it means we only need to traverse only 3 bits to find the value of 5. Similarly, if the number is 8, then this is the binary representation of 8, and if we find log of 8, we get 3, and plus 1 is equal to 4. It means we need to traverse 4 bit to find the value of 8. Okay, cool. Now let's move on to next fact. The next fact is when we divide any number by 2, the rightmost bit shifts or go away. So example, let's say we have 5. And the binary representation of 5 is 0101, right? So when we divide 5 by 2, we simply get 2, right? and the binary representation of 2 is 0 0 1 0. It means this bit is gone now, or we can say this bit shifted to right, and all the remaining bits also shifted to right. So we get 0 0 1 0. And if we again divide 2 by 2, we get 1, and the binary representation of 1 is 0 0 1 0. So now this bit shifted to right, and if we again divide 1 by 2, we get 0. Now this bit shifted to right and we get 0 0 0 0. So this is a technique we use to traverse all the bits of a number. So this is all about the facts. Now let's understand what approach we are going to use to solve this problem. Okay, so this is little bit critical, so make sure you watch this approach carefully. Okay, so let's say we have x is equal to 3 and n is equal to 5, and we want to calculate 3 to the power 5. Okay, so let's start with the 5 first. So what is the binary representation of 5? It's simple, 0 1 0 1. Okay, here first bit representing 2 to the power 0, second bit representing 2 to the power 1, and so on and so forth. And the value of 2 to the power 0 is 1, 2 to the power 1 is 2, and so on and so forth. Correct? Now can we write 5 is equal to 4 plus 1? Obviously, 5 is obviously equal to 4 plus 1. Now if you want to calculate 3 to the power 5, can we write 3 to the power 4 into 3 to the power 1? Right? Because 3 to the power 4 into 3 to the power 1, it's same as 3 to the power 5, because in multiplication the power gets added up, right? Now look at this carefully. In binary representation of 5, this bit is set and this bit is also set. Now if we found value of this bit with respect to 3 and value of this bit with respect to 3, we get our answer, right? How? See, the value of this bit is what? 4. So if we calculate 3 to the power 4 and multiply it with this bit, and the value of this bit is 1. So the value of this bit is going to be 3 to the power 1. So if we multiply 3 to the power 1 with 3 to the power 4, we get 3 to the power 5, right? And we are doing this only for the set bits. We are simply ignoring the unset bit, right? Now the question is how to find 3 to the power 4 and 3 to the power 1. So this is pretty simple, right? So here you can see that every next value is the square of the previous value. So it means if the initial value is 3, then the next value is going to be 3 to the power 1 to the power 2. It means we are simply squaring the previous value. And the next value is going to be 3 to the power 2, power 2, and so on and so forth. So the value of first bit is going to be 3, value of second bit is going to be 9, value of third bit is going to be 81, and value of fourth bit is going to be 6561, right? And we only need to consider set bits. So the value of set bit comes out to be 3 and 81, and if you multiply 81 into 3, we get our answer, that is 243, and this is actually the answer of 3 to the power 5, right? Okay, let's understand again this with different inputs. So let's say if x is 3 and n is 10, 3 to the power 10 is what? Let's see. The binary representation of 10 is what? 1010, and each bit is representing the power of 2. It means this bit represents 2 to the power 0, this bit represents 2 to the power 1, and so on and so forth. So it becomes 2 to the power becomes 1, 2 to the power 1 becomes 2, and so on and so forth. So can we write 10 is equal to 8 plus 2? Yeah, this is correct. 10 is equal to 8 plus 2. So if we want to calculate 3 to the power 10, then can we write 3 to the power 8 into 3 to the power 2? This is also correct, because when we do multiplication, the power gets added, right? So far so clear. Now in case of 10, the second bit is set, right? And the fourth bit is set. So when we multiply the value of fourth bit with the second bit, we get the 3 to the power 10, right? So this So now how to calculate the value of each bit? Let's say the value of first bit is 3. So simply square this bit, we get the value of second bit, right? And so on and so forth. And at last, we just multiply the value of this bit into this bit. So what is the value of this bit? It is 3 to the power 4 to the power 2. It gets 36561. And 3 to the power 1 power 2 gets 9. So when we multiply this with 9, we get our answer, and this is the value of 3 to the power 10. So this is the idea we are using. So here we are going to use two variables. See, the first variable is going to be our result variable, and that variable is used to include all the values of the set bits, right? We simply multiply it with each other. And we need one more variable which calculate the value of this 3. It means every time it simply multiply 3 with 3. So it means it simply squares the previous value. So let's say the first value is 3, then in next iteration the value of 3 becomes 9, then it becomes 81, and it becomes 6561. And this variable simply multiply the value of set bits. It means 3 and 81. As simple as that. So now you can see this is the final implementation of this problem. So this is a function, binary exponentiation. We call this problem as binary exponentiation because we are simply taking the help of binary representation. That's why we call it binary exponentiation, right? So in first line, we are initializing our results variable to 1, and then we are running a loop while n is greater than 0. It means we run a loop till n becomes 0. And in first line of while loop, we are simply checking if n is odd or not. And how we are checking n is odd or not? It simply means if the last bit is set, it means a number is odd. And how we check if last bit is set or not? Let's say here if we have 2 and 2 is even, so the last bit of 2 is not set, correct? So when we divide 2 by 2, we simply get 0 because this is an even number, right? In case of odd, the last bit is set, correct? So when we divide 3 by 2, we simply not going to get 0. So it means that the number is odd. So this is the same logic we are applying here, that we are dividing n by 2, and if we get 0, it means even, and if we do not get 0, it means it is definitely odd. And if a number is odd means the last bit is set. And if the last bit is set, then we have to include the value of x in our result. As simple as that. And after if condition, we are just dividing n by 2. And after this, we are simply multiplying x with x. So this is the step where we are simply doing square of previous value. If the previous value is x, then we are simply doing x into x. Okay, so now let's dry run this code and see how it works. So let's say the value of x is 3 and n is 5. Now we want to calculate 3 to the power 5. So first, initially the value of response is 1. Now in first iteration, we check if n is greater than 0. Yes, n is greater than 0. Then we check if n is even or odd. So what is the binary representation of 5? 0, 1, 0, 1, and it is a odd number. What we do in case of odd numbers, we simply multiply results with x. So the result become 1 into 3 is equal to 3. And after that, we simply divide number by 2. So now this become 5 divided by 2 is equal to 2. And after that, we simply doing x into x. So the value of x becomes 3 into 3 is equal to 9. And in next iteration, now the value of n is what? Reduces to 2. And it is an even number. So in case of even number, we do not do anything because in even numbers, the rightmost bit is not set. That's why we just skip this number. But we divide n by 2 and get n is equal to 1. And similarly, we do x is equal to x into x. So this time 9 multiplied by 9 becomes 81. Great. Let's move on to next iteration. In next iteration, now the value of n is 1. So we check if n is odd or even. This time 1 is odd. The rightmost bit of 1 is set. So what happens when what we do when the bit is set? We simply do result is equal to result into x, right? So what is the value of result? Previous value of result is 9 and previous value of x is 81. So we simply multiply 9 into x, 9 into 81 and we get 243. And we simply divides n by 2, we get 0 and again multiply x into x, we get 6561. And in next iteration our n becomes 0. So this condition of while loop becomes false and we simply stop and return the value of result. And what is the value of result? The result value is simply 243 and this is the answer of 3 to the power 5. Correct? So this is how this while loop is going to work. Now let's talk about the time complexity of this function. So to calculate the time complexity, we need to first find that how many times this loop is going to run. So it's simple. It directly depends upon the number of bits in binary representation of a number. And how many bits are there in binary representation of a number? It's simply floor of log base 2 of n plus 1. We saw it before, right? That there are log n plus 1 bits in any binary representation of a number. Okay? So it means our loop is going to run log n times. We are simply ignoring 1 because in asymptotic analysis we generally do not care about constants, right? So finally the time complexity of this function comes out to be theta of log n. Okay, now what about the space complexity? So in case of space complexity, we are not initializing any array or any extra space. We simply initializing a variable result and we are simply doing some constant operations here, right? Means dividing is also a constant operation, multiplication is also a constant operation, the if condition is also a constant operation. So we do not have so we are not using any space other than this. So this is a constant operations. So the space complexity of this function comes out to be theta of 1, that is constant space, right? So in previous video we saw that the space complexity was theta of log n, but in this iterative approach the space complexity is theta of 1. It means that this solution is much better than previous solution and it is more efficient than previous solution. Okay, I hope now you have clear understanding about how to find power of a number using binary representation of exponent. This is it for this video. Thanks for watching. See you in the next video.